Thank you. Yeah, so today I'm going to talk to you about a novel data-driven approach for computing the statistics of your chaotic system in terms of a very small number of periodic solutions to the governing equations. So chaos is it's a fundamentally difficult problem characterized by a sensitivity to initial conditions. What's plotted here on the board is a prototypical example of chaos, the double pendulum. I've initialized it in 3 distinct but quite similar initial configurations. And behind each configuration, I've plotted a histogram of where the tip is as a function of time. Clearly, the system is chaotic. As the system evolves, these 3 systems will become dynamically dissimilar. This is crazy. They have become dynamically dissimilar, despite being initialized from very similar configurations. And this is a sort of fundamental property of chaos that makes a deterministic description of chaos very difficult. So let's do a statistical approach instead. Maybe try, yeah, into get this on this side. Okay, so we're going to try a statistical approach. What we're going to do is integrate this system for many, many, many time scales of the dynamics. And you'll see that this histogram will converge across each one of these initial conditions. Each one of these pendula is visiting the same set of states and with the same likelihood. So this is due to a property known as ergodicity that most chaotic systems either have or are presumed to have. And this motivates a statistical picture. If we consider the long time average of any observable A over our dynamics, I guess maybe call it this long time average will be the same across each one of these initial conditions. We've lost our sensitivity to how the system was initialized. We can write this long time average as an integral of our observable A over this limiting distribution, which is called the natural density, when this pops back up. Natural density. Okay, so unfortunately, both of these integral formulations are very difficult to compute in practice. On the right-hand side, we have a natural density that is typically discontinuous almost everywhere. It's defined in a very high-dimensional state space. You can get at it in low dimensions, but in turbulence, you're out of luck. On the left-hand side, we have a long-time average that has to be approximated as a finite time average. And if you want to compute the time averages of observables on the fly, you have to store this trajectory x of tau to disk. That can be gigabytes, if not terabytes of data, in our case, in turbulence. So the goal for this talk is to construct an accurate and computationally feasible approximation of this time averaging operator for any observable A that we give it. So luckily, we're not starting from scratch here. Periodic orbit theory has proven in a very small subset of chaotic systems that an infinite time average can be written as a weighted sum over finite time averages, where these finite time averages are defined over periodic solutions to the governing equations. Because these are periodic solutions, you only have to integrate over a single period of motion to compute the average. So these are finite time. Very easy to compute, instantaneous on your laptop. We haven't done too much here because we've written an infinite time integral as an infinite sum. Luckily, there's another result in periodic orbit theory where if you truncate this sum, it will converge to the true mean exponentially quickly in how many orbits are retained. In other words, this is a very efficient representation of your statistics, and it's written in terms of objects that are computationally feasible to compute. So what does this look like in turbulence? The extension of turbulence has occurred over multiple decades. Periodic orbit theory was proposed in the 1990s. In 2001, Kawahara and Kita were able to show that a single periodic orbit described the statistics of their planar quad-flow within 99% accuracy. And this gave us a lot of hope that a statistical description of chaos in terms of orbits would prove fruitful. About a decade later, Chandler, Lucas, and Kurzweil put this to a more rigorous test. They computed the distribution of dissipation over turbulence. What you're going to see is this, I think it's a black or blue line here. And then they computed the weighted sum of distributions over periodic orbits shown in pink. Comparing the two shows that there's a very large discrepancy. This weighted sum of orbits was not able to reproduce the statistics of turbulence. And this is likely due to there not being enough solutions, and turbulence does not come close enough to them for the periodic orbit theory weights to hold traction. Again, a decade later, in the past 2 years, we've seen an explosion of data-driven approaches to periodic orbit expansions. Gokhan Yalnız in Mudinor's group took a Markovian approach and empirically derived the transition probabilities of turbulence between each of these periodic orbit neighborhoods. The stationary distribution of this Markov model is a good stand-in for the weights in this expansion. Page et al. Took a Markov approach as well, which proved fruitful. They also computed the weights as an optimization problem. They asked, can we optimize these weights to minimize the discrepancy between these two distributions? And as you can see, that worked fairly well. However, there are two potential issues with these approaches. The first one being, if you train the weights on an observable, this introduces potential bias into the solution. You can imagine training on some observable a squared. And if you do that, those weights might not be a good estimator for an observable sine of a. You're losing information by training on this. If you take a Markovian approach, you have to treat the orbit neighborhoods as being distinct. Any point in the state space contribution to the time average will be related to only one orbit. And this is somewhat at odds with recent results in turbulence showing that the instantaneous evolution is described by multiple periodic solutions at once. So let's update our goal for this talk slightly. We still want to be accurate, we still want to be computationally feasible, but we want the weights to be observable agnostic, and we won't require them to be Markovian. So how do we do this? I'm going to show you how to do this in the Lorentz system. I think this is the most didactic approach because we're going to use the invariant density itself, and I can actually show you what that looks like in the system. This is the natural density in the Lorentz system. We're going to assume, like all those before us, that we can write infinite time averages as a weighted sum of averages over orbits. This is a linear relationship. The only unknowns are the weights. If we can find p constraints on this linear system, we can solve for the weights through least squares. So consider a Gaussian observable centered at location x in the state space, and take its time average. Given the correspondence of time averages and intervals over densities, we can write this as an inner product of the Gaussian with our natural density. This is nothing more than a convolution of our natural density with a Gaussian window function. So we can think of it intuitively as a coarse-grained density evaluated at position x. On the left-hand side, we have something very computationally feasible and computable. On the right-hand side, we have a relationship to our natural density itself. So, plug this Gaussian into our linear relationship, and we get a linear relationship of coarse-grained densities. On the left-hand side, we have this turbulent coarse-grained density. On the right-hand side, we have orbit coarse-grained densities. Notice that at every location x in the state space, multiple orbits can contribute their statistics. We are no longer invoking disjoint neighborhoods of orbits. Furthermore, we are observable agnostic. If this if this equation is true exactly, we can compute any observable that is a Gaussian mixture, which is fairly fantastic. We don't care about every point in the state space. We only care about positions on the attractor. So let's sort of coax to be on the attractor by taking the inner product of both sides with a blurred density of orbit q, which we know is embedded in the chaotic set. This results in a linear system of equations that we can solve for our weights. The components of the matrix A tell you the overlap between orbit P and Q. Due to the correspondence between densities and integrals in time, we can rewrite this as an integral over the periods of both orbits. This is, again, a finite time average, very quick to compute on your laptop. The components of the vector B tell you the overlap between the qth orbit density and the blurred natural density. This does result in an infinite time average, which we will have to compute as a finite time average. You don't have to store the trajectory here. You can do this in an online streaming fashion. You can also do this in parallel on multiple cores. I like to think of this as compressing the statistics of chaos into this little row vector, which you can then rehydrate through this matrix A and knowledge of the observable values over your orbits. When you compute B to some resolution tau, it'll be correct with an error proportional to tau squared. And the solution to the system we call the least squares weighting of the orbits. I hope you're asking me at this point, how well does this method actually work? So let's compare it against periodic orbit theory. We talked about periodic orbit theory not working in turbulence. It works very well in Lorentz. It's sort of the golden standard in Lorentz. So we picked two observables here, the state space speed, v, and the distance to an equilibrium in the Lorentz system, d. And we plotted the relative error of the truncated expansion versus the true average in this system. The relative error of periodic orbit theory is shown in black, and you can see that characteristic exponential convergence of this theory as more orbits are added. In yellow is our least squares weighting, and there's sort of two takeaways here. Not only do we typically perform orders of magnitude better than periodic orbit theory, but we converge faster. So we're able to achieve a 1% relative error within 10 orbits. And this is important because typically in turbulence, you have only about 10 orbits. So we think this data-driven method could prove useful for this turbulent regime. You do see the method asymptote to a dashed line here. This is 1 over tau squared. So this is the error to which you computed your vector b. This is totally decided by you, and you can set this asymptote to be as low as possible. If the next person wants to come up, by the way, feel free. But in summary, we've computed chaotic time averages in terms of very few periodic orbits. We found that our least squares weighting converges faster than periodic orbit theory, which is treated as the golden standard. And we found that our least squares weighting is agnostic to specific observables. I'd like to thank my collaborators here, and then also mention my colleague Dimitri, who's looking for a postdoc at the moment, has a talk, I think later on Monday or Tuesday. Thank you.